So what we're talking about today is rook theory. What's rook theory? Rook theory is the idea of taking an n-by-n chessboard and putting some rooks onto it and thinking about different possible patterns that you could do. Of course, if I'm putting the rooks on the board and there's no constraint, it's sort of a boring problem. But now if I add in the non-attacking condition, which is generally what we do, that's an interesting constraint. So we're looking at putting non-attacking rooks, and I'll explain what that means in a second, non-attacking rooks onto a chessboard that, let's denote it as n by n. Okay, so here's a 4x4 example, and what do I mean by non-attacking? Well, think of not the colors, because I didn't happen to have 4 of the same color, but think about how rooks move. Rooks move in in columns and in rows. These two rooks, the two black rooks, are attacking. None of the other pairs of rooks are attacking, but these are attacking because one could capture the other. So if I wanted to mix things up a little bit, I could put this rook here, and now I have a non-attacking configuration. No pair of these rooks is attacking. This is easily seen to be equivalent to permutation matrices, right? If I think of all the empty cells as 0 and all the occupied cells as 1, then I exactly get a permutation matrix. I have 1, 1 in every row and every column. Okay, so that's sort of the basic idea of what we're going to be looking at, but let's make it a little more interesting. So rook placements are about restricted permutations, and the restriction comes when we take some kind of subset of the ambient chessboard that we have. We'll call this the board B. And what I'm going to think of for this, let's move our rooks out of the way, is I'll mark certain cells that I'm allowed to put rooks on, so, or maybe not. So these are going to be some cells of my board. Okay, so there I picked 5 squares. This is the board that I'm looking at. And then I can look at things like the rook numbers. So what's a rook number? A rook number, this is going to depend on K. It also, of course, depends on the board that I've chosen here. This is the number of ways to place K non-attacking rooks on B. So number of the ways to place K non-attacking rooks onto B. So that's an interesting thing that we could look at. So let's write down what those numbers are. So if we're taking this board that we have as an example, let's do the computation. So of course we can have 0, and apparently my board runs out at 5. So let's start with 0. How many ways can I place 0 non-attacking rooks onto this board? Well, there's one way to do nothing. So 1. How many ways can I place 1 non-attacking rook onto this board? Well, I could choose any of these cells. If I only have 1 rook, it's automatically non-attacking, so it's just the size of the board. In this particular case, I've chosen a subset of size 5. How many ways can I place 2 non-attacking rooks? So there are lots of ways to do it, right? I can sort of think about this and this and this, and if I move this one around. So we could think about it in a couple different ways. We could think about just choosing 2 elements out of B and then subtracting the ones that we don't want to take. And maybe that's the right way to think of it, as sort of an inclusion-exclusion. So I have 5. So ostensibly, I get 5 choose 2, right? So I can think of it as 5 choose 2. But what do I not get to do? Well, I can't put the 2 rooks here and here. That would definitely be a problem, and I can't put them here and here. So other than those 2 solutions, everything seems to be fine. Those are the only 2 that aren't going to work out for this particular example. So 10 minus 2 is 8. Great. What if we're going to put 3 non-attacking rooks? Now it's going to be a little more dicey. So we could just start out and say, okay, suppose the first 2 are occupied. How many ways could I do it with the third? I could go here, here, or here. That gives me 3 possibilities. Okay, that's if these 2 are occupied. So what if this one's, let's say the first cell, let's leave it here, and let's say this guy goes here. I cannot put this one here. I can't put this one here because I've already counted that possibility, but I can't put it here. I can put it here, so that only gets me 1 more. Okay. And we can see that by placing this rook here, I could actually just restrict the size of my problem. And that's going to give us a nice recurrence if you want to think about that. But okay, that's the way I could do it. And then I've got to have the 3 rooks. So if I say I don't have a guy there and I don't have a guy here, I'm kind of screwed. So that's it for this guy being in this occupied position. So if no one is here, this could be here. I am not allowed to go here. I can go here. And that's it. So we only get 1 more possibility. So this is equal to 5. All right, what if I want to place 4 rooks? Well, I've already got 3 on the board. Where can I put the 4th? I could put it here. That gives me 1 possibility. And notice there's nothing I can do with this cell. Because if I'm going to have a rook in one of these two positions, I can't have it here. And I actually need both of these positions to be occupied in order to have any kind of flexibility in any room. So the answer here is 1. And now, of course, I only have 4 rooks, but I have a 4x4 board. So for n greater than or equal to 5, I'm not going to get any rook placements. And now let's notice this is actually a really nice unimodal sequence, 1, 5, 8, 5, 1. So these rook numbers are particularly nice. And what we're going to be interested in is sort of counting things with these rook numbers, but there's another set of numbers that I want us to think about, which we'll call maybe n sub j. So this is a slightly different number. So this is going to be the number of ways to place as many rooks as possible. So n rooks with j rooks on B. So this is a little different. It's obviously related, but it's different. So now what I'm doing is I'm putting all 4 rooks onto the board, but I can put them anywhere I want, well, within reason, right? And I'm counting how many times do I intersect my board B. So that's what I'm counting. So here, my n numbers are going to be a little bit different. And let's see what this sequence looks like. So let's go with nj. So again, I'm going to have to say, I do have 5 cells on my board. So in theory, I could intersect all 5, except that the most I could have with non-attacking rooks is 4. So again, I'm going to stop at 4. So how many ways, maybe it's easier to start at the bottom here. Can I place 4 rooks on the board and 4 of those cells are in B? Okay, well, I can do it this way. That's 4 non-attacking rooks that are on the board, and it intersects 4 cells. And again, as we've argued here, if I put a rook here, I'm not allowed to put a rook here or here. So then I'm not going to get 4 intersections. So this is one way to do it. Only one way to do it. Now, if I'm going to relax this a little bit and I'm going to say, all right, I'm allowed to intersect in 3 cells, then I can, exactly 3, then I can put a rook here, and then this rook could go here. That's the only place he could go if this guy's here. So that's a valid rook placement. And that's it, actually. So if you want to think about it a little bit more, I could put these guys here. And now I can't put this guy here. I have to put him here. Once I pick these 3 cells, I'm forced by the non-attacking condition to put a rook here. So if this is the 3 in my subset that I pick, there's no way to do it. And similarly, any 3 that I pick on the diagonal forces me to be the identity, right? It forces me to have everything on the diagonal. So the only way I can get exactly 3 is in this way. Okay? So maybe let's jump back to 0. Let's avoid the board entirely. Okay, so now I'm going to compute n sub 0. How can I avoid the board? Okay, well, I could put a rook here and a rook here, and maybe leave that rook here. No, I can't leave that rook here. And then I can sort of just puzzle this out and say, okay, well, that's one way to do it, right? So that certainly avoids my board. And now I can think about like the different regions and say, okay, well, I put this guy here, and then I can kind of count all of my possibilities. And it's all the ways to avoid the board. And I'll tell you that there are 6 ways to do it with this board. There are 9 ways to do it so that you hit exactly 1 cell. And there are 7 ways to do it so that you hit exactly exactly 2 red dots. So these numbers are a little more annoying to try to figure out. You kind of have to play with the possibilities. So I'll leave it as an exercise to confirm these numbers for this board, but let's just look at the contrast. Here we have this lovely pattern 1, 5, 8, 5, 1. It's nice, it's unimodal. Here we have 6, 9, 7, 1, 1. It's kind of a mess. So the next thing we'll do is we'll talk about the relationship between these 2 concepts.